Hi all, happy Sunday slash Monday. I am going to make a video addressing some of the questions that came up in our last, technically it's like two chapters from the Klein book, or two chapters from the Solomon book, one chapter from the Klein book, but it's more about when ketones attack. So in this chapter, I believe it's chapter 19 and 20 perhaps. I don't know off the top of my head, but we're going to talk about, I really want you to be able to see as I'm writing. I think that's good. We're going to talk about everything we've gone over in this chapter, and then, so first we're going to talk about the content of the chapter and how I organize it. And I did some of this already in my video where I went over like alpha additions and aldol condensation and stuff. I'm going to go over that a little bit more. And then I'm going to go over how you can tell what reaction is happening. I just have a few tips and tricks for that. So that's kind of the plan for this video. So overall, what we've learned about in this chapter is formation of the enolate. And specifically regarding formation of the enolate, we've learned how to choose a base. And that's based on just like comparing the conjugate acids of one to the other. So if you have your ketone plus a base, that will give you your enolate plus a conjugate acid. And you can compare the pKa's of the acid and the conjugate acid. And the weaker acid is favored. So, whatever side the weaker acid is on, that's the side of the reaction that's going to be favored. And then we also talked about additions at the alpha position. And when I say alpha, I mean we have our ketone. This is the alpha. I never can remember how to do beta. And then gamma position. So we have alpha, beta, gamma. It's just a Greek alphabet. So it's one away from wherever the carbonyl carbon is. So additions at the alpha, we have acid catalyzed. And a lot of times, as I went over in my other video, that's used to, after the acid catalyzed halogenation. After that, there's usually a base added to undergo elimination reaction. So that'll set up to make one, what is it? It's like the alpha beta unsaturated. So you get you'll get a halogenation form there, and then if you add a base to that, it'll undergo an elimination reaction, and you'll get this alpha beta unsaturated ketone. Usually. So the acid catalyzed halogenation is just this, but a lot of times you'll see this afterwards. And then we have base catalyzed halogenation. And a lot of times, and I go over these all in more detail. I'll do this. I go over these all in more detail in the other video, but just to give you a quick review, a lot of times that will actually keep happening if you have base catalyzed until you get 3 halogens added on, and then it'll undergo a haloform reaction where you have CX3Br or whatever minus, and then you add acid, so you get chloroform, iodoform, or bromoform plus carboxylic acid. And then we also have alkylation, which is basically just an SN2 reaction where you get your enolate and then you react it with some kind of alkyl halide, and you'll have basically this attacks and kicks this out, and you add your R group on there. So all of these, the enolate forms and then attacks the halogen, and that's essentially kind of an SN2 like reaction, but this is the most obvious one. So those are the additions at the alpha position. So we've gone over formation of enolate, how to choose a base, which one's the most stable, and then we went over additions at the alpha, and then we have some condensation reactions. So for condensation reactions, we have aldol, which can happen with ketones or aldehydes reacting with themselves. So, or with another ketone or aldehyde. So that's the biggest thing about aldol condensation is that it's reacting with another ketone. And then Claisen condensation is very similar, but instead of reacting with another ketone, it's esters reacting with themselves or with another one. And then we also have, I'm going to go in these a little bit more detail, 1,2 and 1,4 addition. And this is sometimes called Michael addition, and we'll go on these in detail. And then the very last thing is Robinson annulation, and I'm not going to go over this in too much detail, but it's basically just a Michael addition followed by an aldol condensation. So I'm really not going to cover this in too much detail, but I am going to go over these three in more detail, and then I'm going to talk about how you can tell what you're looking for. So how are you going to know what basically you're going to get? Okay, so in my other video, I'll link to it below. I went over this already, and I went over this in detail, and I just touched on the beginning of aldol condensations and Claisen condensations, but I'm going to go over those again for you. So aldol condensations, they happen with, it can be with itself or with something else, but basically if you have the possibility of forming an enolate. So that means you have to have an alpha hydrogen of some kind. And you can have multiple, or you can just have one. Either way, this will work. And it can react with itself, or can it react with something else? But if you can get the basic one down, just having like R1 and R prime, I think that's going to be best. So if you could have R1 and R2, and then R3, I think that will be a good place to start. So essentially you react this with base. So a good way to look out for an aldol condensation is if you see a ketone or an aldehyde by itself with a base, a lot of times that's going to indicate an aldol condensation. But if we have OH minus here, that's going to create your enolate, O minus with a double bond right there, plus H2O. And then I like to draw this recovering because for me, it's easier to visualize. Sorry, this is R1. It's easier for me to visualize this being the attacker. And once you're used to this, I just hop straight into making my carbon ion. And then that's going to attack here. So we'll come in and attack, and it'll kick up. You've seen that reaction happen over and over again. And I think sometimes where people get a little confused is right here. So the bond goes from this carbon to this carbon. So if we're numbering, this is 1, 2, 3, 4. 1, 2, 3, 4. And that has the O minus where it kicked up. And then R3 is on there and R2. They're both on there. So from here, if there's no heat added usually, or you can also let it just run for like 48 hours and then that would work. But if it's a short time period and no heat is added, you'll you just have an alcohol, and that's an aldol addition. But then if there's heat or if the reaction runs long enough, what happens is a base can come and take this hydrogen and it'll go here and kick this up. You basically lose water. And you end up with, let's see, that was R1, R2, R3. So R3 and R2, and you just have to pick the lowest energy conformation of those. So just like cis versus trans, whichever one is going to be lowest energy conformation, or if you could have, taken from somewhere else. But for the most part, just try to find the cis or trans lowest energy conformation there. So that's aldol condensation. So basically, we get an enolate forms and it attacks the carbonyl group, and then it loses water to get this alpha beta unsaturated ketone. So that's an aldol addition, followed by the condensation. Now, back to our list. We talked about aldol reactions, or them reacting, or ketones or aldehydes reacting with themselves. I do want to note you could have crossed aldol reactions. This is kind of a good option for a crossed aldol reaction because you only have one place where an alpha hydrogen could be taken. But if you have something like this for a crossed aldol reaction, now you have 1, 2, 3 places that an alpha hydrogen could be taken, and you get so many products. You get this reacting with itself. You get this reacting with this. You get this reacting with itself. So you at least get, let's see, 1. Oh, and it could react from either side. So this right here would give you 2 products. This reacting itself would give you the 3rd, and then these reacting together would give you 4th and 5th because it can attack from either side. So if you're going to do a crossed aldol reaction, it's better to do it where there's a very clear alpha hydrogen available to take and really only one. So you want them to be pretty highly substituted. But they can react with themselves or with others. So in a way that a lot of times I'll see something like for an aldol reaction, something like this. And I usually see it and I'm like, what's going to happen here? Because if this attacks and this kicks up and then you just have this, the only thing that could happen is either this could get acid added to it or this will come back down and kick this back out. And so I'm like, nothing will happen here. And then usually it will just take me a minute to realize like, oh, this is not going to do a 1,2 addition. It'll form an enolate and it'll react with itself. So that's something that kind of I think is like something to look out for if you get to a point and then you're like, I don't know what else would happen here. And you don't have any other reactions, you just have an aldehyde or a ketone with a base, that's a good indicator that's it's an aldol of some kind. Okay, so now we've talked about aldol additions. Let's talk about Claisen condensation. Claisen condensations are very, very similar. Basically, instead of just an R group over here, you have an OR group. So I'm just going to have the generic it reacting with itself. And it's a good idea usually to get your enolate by reacting it with whatever this R group is, if it's reacting with itself, by doing that so that this reaction will just get you back to itself, right? So because technically if you had this nucleophile, it can attack and substitute out, but if you have 2 that are exactly the same, it won't change what you have. So that's why a lot of times you'll see, like if this is an ethyl group, you'll have ethoxide. So if you reacted this with ethoxide, you'll get your enolate. And again, it's going to attack at the carbonyl carbon for the other one. So you have OR, and this will say 1, 2, 3, 1, 2, 3, and it bonds to carbon 4 here. 4 has the O minus on it, and then we have OR, and we have a methyl group. And then this is where things change. You could, in theory, add an acid here and protonate this, but for the most part, this would come back down and kick this out. And then you end up with, because this is a pretty good leaving group, so you end up with just one ester on one side and a regular old ketone on the other. And that's sometimes called a beta diketo ester. Beta, because it's at the alpha beta position. Diketo, because it's 1,2 ketone ester. And this, you could stop it here and technically get the right answer, but if you're wondering about what the driving force is, because in equilibrium, technically this wouldn't go forward. So you have to have two hydrogens, or at least one more hydrogen available here, because technically in an acid-base reaction, you would get this abstraction, and it would form this. And actually, this product with your R group is favored. So the formation of this enolate is actually the biggest thing that drives this reaction forward. I don't think you need to super know that, and I talked about it in my last video as well. The biggest thing is you just have to know there needs to be two hydrogens at the alpha position initially for this to work. And again, you can do self like we did here. You can do cross with two different esters or the same, and all of that will work. Again, it's ideal if you're doing crossed for you to absolutely know where the alpha hydrogens that are able to react are going to go. Okay, so that's Aldol and Claisen. That's a quick review of those because I did cover them in my other video as well. And now we're going to talk about 1,2 and 1,4 addition. And I hate the name 1,4 addition, and I'm going to tell you why. So if you have an alpha beta unsaturated ketone, then you can do either a 1,2 or a 1,4 addition. So I'm going to number, I'm not doing IUPAC numbering. I'll do a different color. 1, 2, 3, 4. Okay. So if you have a nucleophile, it can do one of two things. It can either attack here, this will go over, and this will kick up, and you'll get your nucleophile, your double bond here, and an O minus. And then you can add acid and you'll get OH. And hopefully this looks familiar to you. This is an enol. And this is also, this reaction is called a 1,4 addition because we had the hydrogen at position 1 right there. And at position 4 right here, the nucleophile added, right? So 1,4 addition is what this is called. So when we numbered it here, 1, 2, 3, 4, position 4 got the nucleophile, position 1 got a hydrogen. What's annoying about this, however, is hopefully you remember that ketones, for the most part, there's a few exceptions, and we talked about that also in the last video, are more stable than enols. So the next thing that happens is it's actually going to undergo the keto-enol tautomerization to become this. And that's really frustrating. Oh, with your nucleophile here. And that's really frustrating because then what it really ends up being is a 3,4 addition. Because 1, 2, at the end of everything, go back to what they started as. So 1,4 additions actually, I think, would be better called 3,4 additions because ultimately, although in the first step there's a 1,4 addition, ultimately the only place that there's an addition is you get your hydrogen here and you get your nucleophile here. So that's something that I think consistently confuses students, where it's actually like, this is something that you have seen many, well, I guess not necessarily this many times before, but like, it's just hard to recognize what's happening when it's called 1,4, but it adds ultimately at the 3,4 position, and it's all about that enol to keto tautomerization. So If it's easier for you when you're on an exam to look at this and think of it as like 3,4 addition, I support that for you. 1,2 addition, on the other hand, is, I'll draw this in another color. Let's see. If your nucleophile, this one you have seen over and over. Let me get this sort of organized. If your nucleophile attacks right here and this kicks up and you get O minus with your nucleophile down here and your double bond is untouched. So at the, and then you add acid and it becomes OH with a nucleophile. So you've seen this many times before. Basically, we get an addition of the hydrogen at position 1 and the nucleophile at position 2. So this one you have seen many times before. This is just like when we react Grignard reagents with carbonyls. It basically just ignores this unsaturated position altogether. So that's the difference between 1,2 and 1,4. Really, it would be better named, I think, 1,2 and 3,4 addition. But what can you do? I didn't name them. I just tell them these in my brain. So you've seen these a lot, and you have not seen that as much. I'm going to redraw it again for you. So if you have 1,4 addition, it attacks here, goes here, kicks up. Here, I'll draw it again in red. Nucleophile attacks here at the 1, 2, 3, 4 position. This moves over and this kicks up. So then you end up with your nucleophile has gone here and this double bond has shifted over. And then we'll add acid. And that's where your 1 addition comes in. So you get your H and your nucleophile. So at this point, the hydrogen has added to position 1, and the nucleophile has added to position 4, and then it undergoes a keto-enol tautomerization, and you basically just end up with this, the nucleophile here, and the hydrogen has moved over to carbon 3, and so really you get a 3,4 addition. And then on the other side, a 1,2 addition. You've seen this many, many times before. The nucleophile attacks and this kicks up. And so you get O minus with your nucleophile attached here. And then if there's not a good leaving group, you add acid and you get OH and your nucleophile, and this double bond over here is basically untouched. So you can see the hydrogen added at position 1 and the nucleophile added at position 2. Okay, so how do you know when you're going to get which one of these? Stronger nucleophiles tend to favor 1,2. And weaker nucleophiles tend to favor 1,4. If you have an enolate, that's attacking. So if your nucleophile is the enolate that's attacking, so at this point, like the thing that attacks, if it's another enolate, like with Aldol and Claisen type condensations, it actually gives you a mixture of 1,2 and 1,4. If it's a stabilized nucleophile, and hopefully, or a stabilized enolate, hopefully you guys remember what that is. It's when there's another electron withdrawing group here that makes this slightly a weaker acid. It's slightly more, or a weaker base, a stronger acid. This is weaker, so this actually will favor 1,4. So, and let me talk about this for a minute. So this is kind of in the middle of a strong and weak nucleophile, right? Because if you think about your scale of strong nucleophiles, like this is a pretty strong nucleophile. The conjugate acid pKa of that is 16 to 18. This conjugate acid pKa is about 20, right? So weaker acid, stronger base. So if this is the weaker, wait, hang on. Let me think here. I think this was kind of a bad example. So I'm just going to focus between these two. So if you think weaker acid, stronger base, the pKa of this is closer to 10. So this is a weaker acid, and this is a stronger acid. So this is a stronger nucleophile because it's a weaker acid. So it's going to give you a mixture of 1, 2, and 1, 4 because it's stronger nucleophile, not as strong as some other nucleophiles that we've seen, but it is a slightly stronger nucleophile. So it's going to be a mixture between the strong and weak nucleophile option. So you'll get a mixture of 1, 2, and 1, 4. If it's a stabilized enolate, which means it's more acidic of an enolate because it has another withdrawing group, so it can stabilize these electrons left behind, that actually makes it a weaker nucleophile, right? Because this is conjugate acid is a stronger, the conjugate acid of this is a stronger acid, which means it's a weaker base. So it being a weaker nucleophile means it's going to favor 1, 4. So if you're not sure which product you're going to get, the stronger the nucleophile, the more 1, 2, the weaker the nucleophile, the more 1, 4. If you're not sure about the strength of the nucleophile, I would compare the pKa of the conjugate acid. So sometimes 1, 4 addition, I think specifically with a stabilized enolate, is known as a Michael addition. So that weaker nucleophile is called a Michael donor. So 1, 4 addition with stabilized enolate is a Michael addition. It might be any, honestly, any 1, 4 addition is a Michael addition, but a Michael donor is one that causes the 1, 4 addition. And a Michael acceptor is essentially just a ketone that gets attacked, the one for the alpha beta unsaturated ketone. So this would be a Michael acceptor, basically anything that is eligible for a 1, 2, or 1, 4 addition, the alpha beta unsaturated ketone. And a Michael donor is just a nucleophile that's going to favor 1, 4 addition. So Dr. Corrales did not emphasize knowing these names. You might need to know them for ACS, but essentially all that a Michael addition is just a 1, 4 addition, and it's using a stabilized enolate, so, or a stabilized ketone that emphasizes the 1, 4. So sometimes, though, what you want is not to have to use this. You want to be able to use something like this and have a higher priority for 1, 4. And when you're doing that, if you just use this enolate and we react it with LDA, or this ketone, react it with the LDA to get our enolate, right? And then you are attacking in alpha beta unsaturated, you'll get a mixture of 1, 2, and 1, 4, O minus, with your nucleophile right here. And then eventually that will end up as, after undergoing the keto-enol tautomerization, you'll get something like this. Oh, I think I didn't draw that quite right. It should be 1 away. So bond forms right here. This is where numbering your carbon comes in handy. 1, 2, 3, 4. So it would look something like this. Let me do that over again. So you'd get a mixture of 1, 2, and 1, 4. And at the 1, 4 position, it would essentially look like this. Initially, it would be hydrogen with a double bond here, but then it undergoes a tautomerization. A 1,2 addition would look like O minus. This methyl group would still be there, and this other one wouldn't be impacted. And then we would add acid, and that would become an OH group. So this would be a 1,2 addition, and this would be a 1,4 addition. And if you just did these reaction conditions here, you can ignore my mess up. If you made this into an enolate and then you had it react with this, you would get a mixture of this, and it would be a mess and really annoying to clean or purify and only get the thing that you want. So somebody figured out that if you turn this into an enamine, you can make this a weaker nucleophile, and it will give you primarily 1,4. So if before you turn this into an enolate, if instead you react it with NR2, you'll get NR, and this is an enamine reaction that we covered in another chapter, so I would not stress out about that right now. Hopefully you remember how to do it, but essentially if you do the ketone plus NR2, you get this, and then this can attack, and it will favor a 1,4 addition if that's what you're looking for, if that's the thing that you want. So say you really want the 1,4 addition instead of the 1,2 addition, this will come down and this will attack as your nucleophile, and you'll get O minus with a double bond here. And then this, I'm going to number my carbons because it's always a mess. 1, 2, 3, 4. Okay. So this is carbon 4. It made a bond with carbon 3. And then 2 has this double bond to nitrogen, which is positive. So we will get only the 1,4 addition. And then when you add acid to turn this to alcohol, it will actually also turn this back into a ketone. If you remember, that's what happens. That's enamines are reversible formation. And then the keto-enol tautomerization will take place. So you'll end up essentially with this. So this basically, the stork enamine reaction is just a way to force it into a 1,4 addition when you maybe wouldn't have gotten that otherwise. So I'm going to give you another example of that. If I wanted to react, let's do this ketone with this, I would get a mixture of products, right? I would get the 1,2 and 1,4 addition. But if I instead, I reacted this ketone with this, I would get an enamine. In with 2 ethyl groups and a double bond over here. And then I could add my alpha beta unsaturated ketone, and it would react from this carbon right here. This would go over and this would kick up. And you would get primarily the 1,4 addition, which would give you O minus there. 1, 2, 3, 4, and 4 bonds with this carbon right here. 5, 6, 7, 4, 5, So we have this, and the double bond moved over. And then when we add acid, it will hydrolyze the enamine back, OH, to a ketone, and then we'll go through a keto-enol tautomerization. So that will turn back into a ketone, and this will stay. So that's essentially a way to get a 1,4 addition of a ketone and making sure that you can favor one over the other. Okay, and then all a Michael addition is basically a, I believe it's a 1,4 addition. It's an aldol condensation followed by a Michael addition. So it's a Robinson annulation. It's just two reactions mixed together, and I don't know why. And it makes a cyclic molecule. I don't think I'm actually going to go over that at all right now because I think it will not be heavily featured on your final. But what I do think will be important is knowing when you can expect what. So that's, let's see. We talked about formation of enolate in an earlier chapter. In an earlier video. We talked about additions at alpha at an earlier video, and this time we went lightly back over Aldol and Claisen and focused on 1,2 and 1,4. I don't think Robinson annulation as important. So that's the content of the chapter. And now, how can you tell what reactions you're going to expect? Well, if you have a ketone with a nucleophile, you'll either get a 1,2 addition, so this one that you've seen over and over before, the nucleophile attacks, this kicks up, and then if there's a good leaving group, the leaving group will leave and this will be recovered, or if not, we'll just add acid and get an alcohol, or you'll get an enolate. Oh, sorry, I guess I should have done. The way you can usually tell the difference between these two is honestly, you'll see really strong nucleophiles favor this. So like Grignard reagents favor that. That's the biggest one I feel like you see a lot is Grignard reagents. And then if it's something like you've seen before in the acetal and hemiacetal where there's an alcohol present and it wants to attack, especially if you have a good leaving group, those are some of the biggest ways that you'll see the nucleophile add. When you're looking for an enolate formation, it'll usually be more like LDA is probably the biggest one that you'll get to indicate that it's going to be an enolate formation. So that's kind of how I tell the difference. And then I also look at what comes next. So is it just only a ketone and a nucleophile, and it's not the kind of nucleophile that tends to attack at the carbonyl center, then you're probably going to get an aldol condensation. It's going to react with itself. So if I saw just this reaction, I would make the enolate, and then I'd be like, what is it going to do now? Oh, well, I guess it's floating around with a bunch of other of these. It must be an aldol condensation, right? So that's kind of how I tell if it's going to be a 1,2 addition or if it's going to be a formation of an enolate. Is I think about the strength of the nucleophile and what context I've usually seen that nucleophile in before. And then I think about what reaction could happen after that. So like if I have this plus acid, I'm like, oh, it's probably going to do a 1,2 addition. If I have this followed by heat, I'm going to think, oh, this is probably an aldol condensation. It's probably an aldol addition followed by a condensation, right? So I kind of look at the context clues to help me figure it out. And then if you have an alpha beta unsaturated ketone, then you know it's going to be a 1,2 or a 1,4 addition. And then you know now that we've talked about it, that a weaker nucleophile will favor 1,4 and a stronger nucleophile will favor 1,2. So if you had a Grignard with this, 1,2 is going to be your best bet. If you had a stabilized enolate, being the nucleophile, it's going to be 1,4. Or if you had an enamine being the nucleophile, it's going to be 1,4. So that's kind of how I tell which one's going to be which. Or if there's an ester, then it's going to be Claisen condensation. That's the biggest thing we've seen with esters, right? If it is an ester and there's some kind of nucleophile, usually in this case, actually, it's going to be whatever your ester is. Like if this is whatever your R group is, it'll be the corresponding epoxide or alkoxide of that. And that's usually going to be a Claisen condensation react with itself. So that's kind of like the context clues I look for to know what it's going to be. I don't have a great set of practice problems to work through that with you, but I am going to post a video of me working through the exam that we just took, and hopefully you can hear some of my thought processes when I look at these questions and how I kind of decide what the reaction is going to be. Okay, well, that's all I have for you today. I hope that was helpful, and good luck studying. Let me know if you have any questions.